So if you've spent any time at all talking to a chatbot, generating code, or just, being amazed by modern AI,
You're interacting with a transformer.
you're interacting with the transformer architecture. It's the engine behind absolutely everything. But that foundational paper, Attention is All You Need, is from 2017.
I mean, in AI years, that's practically ancient history.
It really is. So we're not here today to just reread the paper. We're doing a deep dive into the engineering, the little tweaks and the big strategic shifts that took that original framework and turned it into the LLMs we use every single day.
And that's a key point. The original transformer was built for a very specific job, machine translation. It had an encoder to, read the German and a decoder to write the English.
And the whole magic was that self-attention mechanism, right? The queries, keys, and values.
That was the breakthrough, letting every word look at every other word to figure out what's important.
Okay, so let's unpack that. If that idea was so revolutionary, why have people spent the last, 7 years fixing and sometimes even throwing out parts of that original design?
Well, that's the mission, isn't it?
Exactly. Our mission today is to look at 3 key areas that got a major upgrade. First, how these models understand word order. Second, how we keep them stable when they get ridiculously big. And finally, how we deal with the massive cost of attention itself.
All right, let's get into it. The first big problem the transformer created was actually a side effect of its biggest innovation: parallel processing.
Right, it looks at all the words at once, unlike the old RNNs that had to go one by one.
Exactly, which is way faster. But the problem is if you look at everything at the same time, you lose the sequence. You have no idea what order the words came in. The model doesn't know the cat chased the dog from the dog chased the cat.
So you have to literally inject that position information back in. And the original paper tried 2 ways, right? The first was learned embeddings.
Yeah, learned embeddings. It seems intuitive. You just learn a vector for position 1, a different vector for position 2, and so on.
But that fell apart pretty quickly. Why?
It just couldn't scale. If you trained your model on sentences up to, say, 512 tokens long, it had no idea what to do when you gave it a 600-token document. It had never learned a vector for position 513.
It hits a wall.
A hard wall. So they went with option 2, those very scary-looking sine and cosine formulas.
The ones that look like they're straight out of a trigonometry textbook?
They do. But here's where it gets really, really clever. The breakthrough wasn't about encoding the exact position. It was about encoding relative distance.
Okay, what does that mean?
It means that because of the math, the specific way sine and cosine interact, when the model compares the position of word M and word N, the score it gets is just a function of their distance, of M minus N.
So the magic isn't knowing that cat is at position 12. The magic is knowing that sat is only 1 position away from cat.
You've got it. That's precisely the insight. Our intuition is that nearby words matter more, and this mathematical trick bakes that intuition right into the model. Plus, it can extend to any length you want.
And today, pretty much every modern LLM uses some version of this idea, like ROPE, rotary position embeddings.
Exactly. ROPE takes that core principle of relative distance and integrates it even more deeply by, rotating the query and key vectors based on their position. It's a more elegant way to do the same fundamental thing.
Okay, so that's position solved. Let's talk about stability. You can't train a model with 100 billion parameters if the math keeps, exploding.
You really can't. And that's where layer normalization, or layer norm, comes in. The basic idea is to keep the numbers inside the model, the activations, from getting too big or too small. You just, normalize them at each step.
And I've heard that one of the biggest practical fixes in the early days was just changing where you put the layer norm. The original was post-norm, and now everyone uses pre-norm.
Yes, a huge, huge change. Post-norm means you normalize after the main computation. That works okay for smaller models.
But not for the giants.
Not at all. With really deep models, the values can blow up before you even get to the normalization step, and the whole training run just fails. Pre-norm, where you normalize the vector before it goes into the attention or feed-forward layer, just creates a much smoother, more stable training process.
It's like a safety valve.
It's the essential safety valve for training at scale. And there's an efficiency update here too, right? This move from standard layer norm to something called RMS norm.
What's the difference there?
It's just a simpler, lighter version. Standard layer norm uses both the mean and the standard deviation. RMS norm just uses the root mean square, which is computationally a bit cheaper and requires learning fewer parameters.
So you get pretty much the same stability, but with less technical overhead. trimming the fat.
Precisely. And trimming the fat is the name of the game, which brings us to the biggest hurdle of all, attention's quadratic scaling.
The O of n squared problem.
Yep. Double your input length, and you quadruple your computation time. It's the fundamental bottleneck that stops us from having, a million token context window for every model.
So how do we get around that?
Well, there are two main tricks. The first is to just not let every token pay attention to every other token. It's called sliding window attention, or SWA.
It's like putting blinders on the tokens.
That's a great way to think about it. A token at position 10,000 might only be allowed to look at tokens, say, 8,000 to 9,999. It dramatically cuts the cost.
But don't you lose long-range information that way?
You do, which is why models like Mistral do something clever. They use the sliding window for most layers, but then every few layers they'll have one full global attention layer just to make sure the model can still connect distant ideas. It's a hybrid.
And the second big scaling solution, I hear it's more about memory.
It is. It's about matrix sharing. In the original multi-head attention, or MHA, every single attention head has its own separate unique matrices for query, key, and value. That's a lot of parameters.
A lot of redundancy.
A ton. So now we have things like MQA, multi-query attention, where all the heads share the same key and value matrices, or GQA, grouped query attention, where they share them in small groups.
And the big win there is for inference, right? When the model is actually generating text.
That's the crucial part. It's all about the KV cache. When a model generates text, it saves the key and value vectors it calculates so it can reuse them. If you're sharing K and V matrices, that cache becomes vastly smaller.
Which means less memory, faster generation.
And it means you can run a powerful model on consumer hardware, not just a massive server farm. It's a huge deal for practical deployment.
That's a fantastic summary of the toolkit. So we have relative positions, pre-norm for stability, and these clever attention tricks for efficiency. Now let's see how these tools were actually built into the three big model families we see today.
Absolutely. When you look at the landscape, pretty much every model falls into one of three camps, and they all trace their lineage back to that original 2017 paper.
Okay, let's start with the classic, the full encoder-decoder architecture.
This is your T5 family. T5 stands for text-to-text transfer transformer. The whole idea was to frame every single NLP task, whether it's translation, summarization, or question answering, as a text-to-text problem.
And they had a really unique way of training, right? This span corruption thing.
They did. Instead of just predicting the next word, they would take a sentence, blank out entire chunks of its spans, and replace them with a single special token. The decoder's only job was to perfectly reconstruct those missing spans.
So it's more of a fill-in-the-blanks task on steroids.
Exactly. And it makes the model really good at things like abstractive summarization. But if we look at what most people are using day to day,
it's decoder only. The GPTs, Llama, Falcon, all of them. What was the big innovation in just throwing away the encoder?
Well, it comes down to one critical feature: causal masking.
Causal masking.
Yeah.
That means a token can only see the tokens that came before it, right? It can't see into the future.
Precisely. And that sounds like a limitation, but it's actually the entire mechanism that enables text generation. To predict the next word, you must only use the words you've seen so far.
So that constraint is what forces the model to learn how to continue a sentence, how to write a story.
That's it. Its entire training objective is just predict the next token. And by doing that billions of times, it becomes incredibly good at generating coherent, sequential text.
Okay, so that's the generative family. Let's pivot back to the other major branch, the encoder-only models. I'm thinking of BERT. Why is it still so dominant for, understanding tasks?
The key is in the name: bidirectional encoder representations from transformers. The key word is bidirectional.
Because it doesn't have that causal mask.
Exactly. Since it's just an encoder, a token can look at all the other tokens in the sentence, both before and after it. This gives it a much deeper, more complete understanding of context.
But it also means it's terrible at generation, because it's always cheating and looking at the answer.
Right. It's not a generator, it's an understander. And to achieve that, it had a really specific pre-training setup. It needed special tokens like CLS at the beginning and SEP to separate sentences.
What was the point of that CLS token?
The idea was that after being processed through all the layers, the final vector for that one CLS token would act as an aggregate summary of the entire input's meaning. Perfect for classification.
And it had its own unique training tasks, right?
Yeah.
Not next token prediction.
No, it had two. The most famous one was the Masked Language Model, or MLM. You'd take a sentence, randomly hide about 15% of the words, and force the model to predict them based on the full bidirectional context.
The ultimate fill in the blanks.
The ultimate. And the second one was next sentence prediction, or NSP, where you give it two sentences, and it had to guess if the second one actually followed the first one in the original text.
So if someone today wanted to use BERT for, say, sentiment analysis, how would that actually work?
It's surprisingly elegant. You feed your sentence into BERT, let it run through all its bidirectional layers, and then you throw away almost all the output.
You throw it away.
All of it except for the final output vector of that one special token, the CLS token. You take that single vector, which represents the meaning of the whole sentence, and you feed it into a simple classification layer. And that's it. It tells you positive or negative.
So all that complexity gets distilled down into one perfect summary vector.
That's the power of the encoder-only architecture.
Okay, so we've established these models are powerful, but they're also huge. BERT-based was over 100 million parameters. Efficiency had to become the next frontier.
Absolutely. And that's where models like DistillBERT came in and really pioneered the idea of knowledge distillation.
So how does that work? You have a big teacher model and a small student model.
Right. And you don't just train the small student model on the original data. That's not very efficient. Instead, you have it learn from the teacher.
But it's not just learning the final answer, is it?
No, that's the key. It's not learning the hard label, like this is a positive review. It's learning the teacher's soft targets. The full probability distribution. The teacher might say, I'm 90% sure this is positive, but there's an 8% chance it's neutral and a 2% chance it's negative.
So the student learns the nuance, the uncertainty of the much larger model.
Exactly. It learns to mimic the teacher's entire thought process. And the result is a model that can be, say, half the size with half the layers, but retains 97% of the performance of the giant original. It's a huge win for efficiency.
And finally, we get to Roberta, which kind of proved that sometimes the best innovation isn't a clever algorithm at all.
Roberta is fascinating. It stands for Robustly Optimized BERT Pre-Training Approach. They basically took BERT and just optimized everything. First, they showed that the next sentence prediction task, NSP, was actually not very helpful, so they just got rid of it.
They simplified it.
They simplified it, but the real lesson was about data and training time.
Right. The data increase was insane.
It was. They went from the 16 gigabytes of text BERT was trained on to a 160 gigabyte corpus, 10 times the data. And they introduced dynamic masking, so the model saw a different version of the masked sentences every single time it went through the data.
And the outcome of just more data and smarter training.
A huge performance jump, around a 4% improvement across the board on standard benchmarks, which is massive at that level. It proved that sometimes the answer isn't a newfangled architecture, but just scaling up your high-quality data and being smarter about how you train.
So what we've really walked through today is this incredible, meticulous journey. It wasn't about one single paper tearing everything down. It was about relentless engineering making position relative with ROPE, finding stability with prenorm, and chasing efficiency with MQA and distillation.
The foundation, that core idea of attention, is still all you need. But the execution, the thing that makes it actually work at the scale we see today, that requires constant refinement. It's a mix of mathematical elegance and, as Roberta showed, sometimes just brute force.
This whole evolution brings us to where we are now, with generative chat-focused models being overwhelmingly decoder-only. But that leaves a really interesting niche. So here's a final question for you to mull over. If modern LLMs are all about generation, what fundamental, specialized role does the encoder-only architecture like BERT still play in the world of AI applications today, and why hasn't it been completely replaced?